Hello friends, I welcome you to our ongoing Six Sigma journey, and we are step by step advancing in our DMAIC cycle: define, measure, analyze, improve and then control. So this lecture is 38 number lecture, and I would like to introduce the topic of design of experiment and help you to appreciate the various issues involved in conducting an effective and efficient experimentation. So let us appreciate a beautiful quote given by Albert Einstein: "A theory can be proved by experiment, but no path leads from experiment to the birth of a theory." So this is where the importance of experimentation lies. You can propose a theory, but you need to prove it by experimentation, and then this theory can be well accepted. So we have to appreciate the importance of experimentation in our day-to-day professional life, whether in the manufacturing sector or service sector. Now before I proceed, we are at a particular juncture, and now it's a time to revisit that where we are in our Six Sigma journey. So let us have a quick recap. Quality, fundamentals and key concepts we have discussed in week 1 and week 2, and typically in week 1 we have talked about the various quality aspects, definitions, history of continuous improvement, Six Sigma principles and focus areas, DPMO, DA mode, then first pass yield, and then some of the Indian organizations implementing Six Sigma. Then in week 2 we had a detailed discussion on quality management basics, then fundamentals of TQM, cost of quality, QFD, management and planning tools, part 1, part 2, and then we moved to the first phase of our DMAIC cycle, and that we talked about in week 3. So as a part of define phase, we talked about Six Sigma project identification, selection and definition, project charter and monitoring, process characteristics and analysis, and a very important tool, SIPOC. So this was basically the part of define phase. Then we moved to the second phase, that is the measure phase, and we covered the measure phase in week 4 and week 5. So you had week 4 various learning points. So data collection and summarization, part 1, part 2, measurement system analysis, fundamentals, measurement system analysis, a very important topic, gauge R&R study, fundamentals of statistics, probability theory. Then subsequently in week 5 you had seen process capability analysis, measures and indices, process capability analysis, Minitab application, and then we had seen the non-normal process capability analysis. Then we moved to the analyze phase, and week 6 and 7 we devoted on the analyze phase. So in week 6 we talked about hypothesis testing for single population, for two population. Then we had seen the hypothesis testing, Minitab application, correlation and regression analysis, and regression analysis model validation. Week 7 we talked about one-way ANOVA, two-way ANOVA, multivariate analysis, failure mode effect analysis. That was the last topic we had discussed, and we had seen the importance of such a simple but logical tool in identifying the potential failure modes right at the design concept stage of the process or product, manufacturing or service, and how it can help the practitioners, managers to take some of the corrective measures at a very early stage in the design stage of the product or process. Now with this is the departure now or continuation in our DMAIC, and now we will discuss the improve phase of our DMAIC Six Sigma cycle, week 8 and week 9. So typically week 8 we will begin with this lecture, that is introduction to design of experiment, randomized block design, Minitab application, factorial design, Minitab application. Then week 9 we will devote our time and discussion on fractional factorial design, fractional factorial Minitab application, Taguchi method key concept, and some illustrative application of Taguchi method. So with this, let us try to see that what we would like to appreciate as a part of this lecture, that is introduction of design of experiment. We will see some history of DOE, how the concept has evolved over a period of time, DOE principles and terminology, the strategy of experimentation, what are the key points that as an experimenter you should consider, and guidelines for planning, conducting and analyzing the experiments. So just see this, and what do you appreciate? Can you tell me? So this is the evolution in the concept of quality, and fine, we say that product quality is the first fitness for use, process quality is the fitness for production, quality of innovation, that is the process, quality of organizational design. So this was the period of stability and this was the period of rapid change. So degree of organizational development, and with respect to that my objectives are changing. Now whatever phase you take, when a particular phase, whether it is product quality, process quality, quality of innovation or maybe organizational design, you need to address couple of issues right at the design stage, and when you do so, you actually take the help of design of experiment. So design of experiment is a statistical technique which helps us to address couple of issues right at the design stage, and that is why this discussion, the design of experiment and related topics, we have considered as a part of, or usually considered as a part of, say improve phase of the Six Sigma cycle. So improve right at the design stage, do it right first time. So this is what we have appreciated. Once again I would like to remind you, you should not go away from this particular diagram because this is the crux of this course. Six Sigma means less variability, 3 Sigma means higher variability, 6 Sigma means producing more A grade products, and I am very close to my target and my variability is very less. Even if you compare it with respect to LSN and USL, this Six Sigma process is well within say your LSL and USL. Even if there is a shift in my mean, maybe because of wear and tear, setting in the machine or operator skill or whatever, then also I am in a comfortable zone and my level of rejection would be very less. So this is what we try to achieve through DMA-IC cycle, and design of experiment really helps us to realize our ultimate objective of reducing variability right at the design stage. Now let us see what is DOX or design of experiment. So typically it is an experiment is a test or series of tests you try to conduct. You go to doctor and doctor would ask you to go for couple of tests when you explain your problem, and then you will have the diagnostic report. You will go back to your doctor and then doctor will give you some recommendation, some prescription to improve the status of your health. So basically experimentation is part of your improvement strategy, and when you know exactly what is happening, you can recommend better strategies, better solutions for improving the state of situation. So experiments are used widely in engineering world. Process characterization and optimization, whether my processes are operating at the optimal level or not, I can figure it out by using the design of experiment strategy. Evaluation of materials and its properties, very important. When you look at the material and strength and other tensile strength, compressive strength and other properties, then basically it is an outcome of say composition of a particular say material, and it is important to evaluate the material properties. Product design and development right at the concept stage, component and system tolerance determination, this is also part of my design of experiment. So there is a very good saying that all experiments are designed experiments, some are poorly designed and some are well designed. So you may have your intuitive way to conduct the experiment, you may have your own approach for conducting the experiment. We all in our day-to-day life conduct the experimentation, but whether it's the right strategy or wrong, we many times do not know unless we face the consequences. So here design of experiment is a well developed, statistically driven field which helps us to conduct the experimentation in a systematic step by step procedure, so that we can rely on our output as well as we can take the couple of recommendations and the actions with better confidence. So typically you have an engineering experiments to design, and it helps to reduce my time to design, develop new products or processes, because I have addressed many of the concerns and issues through experimentation. So I can now go ahead with the full-fledged production or the process, and this is where it helps. Improve the performance of the existing processes. Fine, you have a process but there are a couple of problems. You can conduct the experimentation in order to see that whether your process is operating at the optimal parameter setting or not. Improved reliability and performance of the products. Achieve product and process robustness. I must have the product which is extremely less, say, sensitive to the various nuisance factors, maybe the external factors like humidity, maybe the usage condition and many other things. So I need to have the robust product. Evaluation of material design alternative. So typically I have something like this. You have a process, you have the input, you have the output, you will say controllable factors and you will have uncontrollable factors. Let us try to take a live example, spontaneous example of my delivering this particular lecture. Now what are the inputs I am using? I am using the text, I am using the various sources. For example, this particular topic, design of experiment, and other topic, I will be extensively using the book Design of Experiment by Douglas Montgomery, and couple of examples are picked up from this particular book. So these are my inputs. Now I have structured the input, decided my strategy to deliver. It's a process part and I am delivering. What is the output? Output would be a video lecture, a learning material that will help my students, practitioners to digest the concept. Now what are the controllable factors? So in this particular process, controllable factors would be my selection of the textbook, that is in my hand, then preparation of the slides, then examples to be given for a particular slide. All these are controllable factors. Even the selection of my dress, it is controllable. But when I say uncontrollable factors, so let us say there is an electricity problem, or there is a problem with the recording system which is unforeseen, and there could be, or maybe let us say my health is not good. So uncontrollable factors, and your process is to be made immune to this kind of uncontrollable factors, and controllable factors you try to decide the best optimal level so that you get the best output, optimal output in terms of quantity and quality as an outcome of your process. So this is exactly what we try to address as a part of design of experiment. Now I am just giving you another example, that those who are in the manufacturing domain, so manufacturing process of injection molded parts, your mold temperature, gate size, holding pressure, screw speed, percent regrind, type of raw material as the inputs, and as an output you will have length of the mold part, width of the molded part, thickness of the molded part, and percentage shrinkage of the plastic part. So you need to have little bit knowledge of this manufacturing process. If you have, then you can at least appreciate the input and output of this particular process, which is injection molding. So we have the input and output, and we have controllable and uncontrollable factors, and I would like to minimize the impact of uncontrollable factors, and I would like to set my controllable factors at the optimal level so that my inputs can be best converted into the desired outputs. So just see the history of DOX, it's interesting. So it's not that something we are discussing just in last 5 years. You can just see that 1908, maybe 100 years back, people have started working on this, and 1908 to 1940s, even you see the Gosset and t-test, 1908, so that was the initial step in conducting the hypothesis testing and analyzing your experimentation statistically. Then Fisher and the co-worker, they have contributed a lot. Then profound impact on agriculture science. So this was the area where they were very much interested to see the impact of humidity, temperature, fertilizer and the soil. These are the various input factors, and what is its impact on the agriculture produce quality production, and this is where this experimentation strategy has gained lot of importance. Then there was factorial design, ANOVA we have seen. Then industrial era started 1951 to late 1970s, Box and Wilson response surface. So I want to see the response surface of my dependent variable, my response variable, and I want to figure out that what could be the optimal level for operating my process. So this is where some research was done. Then applications in chemical and process industries, that was basically executed. Then the second industrial era, say late 1970s to 1990, quality improvement initiatives in many companies, they adapted the use of DOE, and Taguchi and Roberts design parameter design concept that has evolved as an extension or as an integral part of DOE. And finally there is a modern era 1990 where we are trying to integrate and club various techniques for improving my products and processes right at the design stage, at a very early stage. So let us see how will you conduct the experimentation, what is the planning, conducting and analyzing an experiment, what is the strategy. So let us go step by step. Point number 1, recognition and statement of problem, very important. So what are the factors? Screening or characterization needs to be done for a particular process. You cannot consider all the factors. Optimization, conformation, discovery and robustness, these are the preliminary issues that we try to address at the recognition of and statement of the problem. Means exactly what I want to achieve, what are my objectives, what are the factors that are impacting my system, and what are the new things that I want to discover. Then point number 2, choice of factors, levels and ranges. Suppose you say temperature is a contributing factor, or humidity is a contributing factor, or pressure is a contributing factor, then what could be the ranges of this temperature, pressure and humidity, and these ranges needs to be decided based on your process knowledge, domain knowledge, and then you would like to conduct the experimentation for this. Then selection of response variable, whether I am interested to analyze the yield of the agriculture produce, productivity, surface finish or length of my molded part, what could be the characteristic that I would like to analyze as a response variable. Choice of experimental design. Then 5th is conducting the experiment. So choice of experimental design, depending upon the situation, you have various variety like randomized complete design, randomized incomplete design, randomized complete block design, RCBD, you have factorial design, you have fractional factorial design, you have say Taguchi design, so mixture design. There are various varieties. So depending upon the situation, you choose the particular strategy for conducting the experimentation. So that is the choice of experimental design. Then you actually conduct the experiment and then you do the statistical analysis to figure out that what are the factors that are really statistically important or not. So again, ANOVA we will use extensively, and you have studied the two-way ANOVA analysis, so there would not be much difficulty in conducting this step number 6. Step number 7, drawing conclusions and recommendations and proposing an action plan to the top management. Now please see here that when I am trying to follow these 7 steps up to step 3, you need domain knowledge. So this demands basically the domain knowledge or knowledge of the process or particular problem you are trying to address. And this is where your skill of DOE, design of experiment, will come in picture. So I must say that knowing only DOE will not solve the purpose. You must know the context, you must have a knowledge about the factors affecting, what is the response variable, what could be the possible levels, and once you have this knowledge, then only you can apply your skill of conducting experimentation using DOE, and then you can really conduct a meaningful experiment which can yield some important results. So just see this example of cause and effect, that I want to have a good say blade finish, and let us say I want to see the effect blade profile surface finish defects. I am citing here the controllable design factors: x-axis shift, y-axis, z-axis shift, spindle speed, fixture height, feed rate. You have uncontrollable factors: spindle differences, ambient temperature, titanium properties. You have some nuisance factor which is to be blocked. So we will see what is blocking. So operator, tool vendor, and then you have some held constant factor, maybe viscosity of cutting fluid, temperature of the cutting fluid. So when you think about an experimentation, you cannot just accept all the factors equal. You must segregate them into different categories: controllable, uncontrollable, maybe noise factors, or the factors to be held constant. So we will use this concept as per our requirement, and not necessary that you segregate the factors all the time in 4 categories. If required, you can only say controllable and uncontrollable factors. Now we have already talked about the measurement system, but just I would like to remind you that there is a very good principle to be appreciated, and this is GIGO. GIGO stands for garbage in, garbage out. So if you say have poor data which is an outcome of a very poor or ordinary measurement system, obviously whatever great effort you will put in, your experimentation will lead to the wrong conclusions. So we discussed this part in detail in our lecture, say measurement system analysis, gauge R&R. Here once again I would like to remind you that accuracy is basically your closeness to the measured value or closeness to the target value. Precision means my instrument should be precise enough to reproduce the readings when the same reading is taken again and again, and the closeness among the readings is precision. Stability: over a period of time, if I take the reading, my instrument must remain stable, measurement must remain stable. Suppose I have checked one reading in the morning with vernier caliper, and same reading if I check in the evening, that should not be significant difference. And capability, so your system is capable if the measurements are free from bias. So we had seen the bias that suppose you are taking the temperature reading, the example we discussed previously with the thermometer, then for lower maybe it is taking some higher reading, or higher it is taking lower reading, then there could be some bias, and this bias should also be properly addressed before I start collecting the data for my experimentation. So selection of quality characteristic for industrial experiment is an important issue, and you must see that CTQ, critical to quality, the quality characteristic which is easy to measure and important must be considered. So it should be a continuous variable as far as possible, and it can be measured precisely, accurately with stability. So many times if you choose some very complex phenomena to be measured, then either you need highly precise instrument, or such kind of measurement are not very much accurate, stable, and this can also cause the problem. So it should say quality characteristics should cover all dimensions of the ideal function input output relationship, and preferably be additive. No interaction exists among the quality characteristic. So effect of each factor on robustness should be in a consistent direction even when the setting of factors are changed. So this were the couple of concepts on my design of experiment. Now Taguchi, we will see it in detail, but just to introduce, he proposed a concept of robust design, and he believes that as you deviate from the target, there is a loss to society. It means it's not enough to achieve within specification, but as you go away from the target, your target value, you are basically producing lower quality products, and it's a loss to society. We have seen that 6 sigma spread is very less compared to 3 sigma. My processes in 6 sigma are more centric towards the targeted value, and that is exactly what I try to achieve through experimentation using the Taguchi concept. So there are key points of the experimenter. Use your non-statistical knowledge of the problem, so you must have the domain knowledge. Keep the design and analysis as simple as possible. Recognize the difference between practical and statistical significance. Sometimes you find some p-value, and let us say your alpha, now you are familiar, your level of significance, set level of significance, alpha is 0.05. You have calculated the p-value for a factor, let us say temperature. This is the observed significance level, and let us say this comes out to be 0.001. So this is very less, and you will reject. Now let us see another example where your alpha is same, set significance level which is 0.05. Now let us say your observed level of significance is 0.049. So there is only 1% difference. Now would you like to reject your null hypothesis for such a small difference? For such a small difference in the alpha and the p-value means set significance level and the observed significance level, you have to apply your practical knowledge. Experiments are usually iterative. So I told there are enormous benefits of conducting DOE. It improves yield and stability, return on investment, process capability, consistency, it reduces the manufacturing cost, avoids the duplication, rework, reset can be minimized, and design and development time can significantly be reduced. I would just like to share one statistics that as a rule of thumb, if you are in a typical high-tech industry like maybe laptop, mobile manufacturing, and if you are late by 4 to 6 months in launching your product, then almost you lose 50% of the total profitability that you may realize during the entire life cycle of your product. So just see that you have a product that will go through the inception, then rapid advancement, and then maturity, and then decline. So there is a total profitability, and you lose almost 50% if you are late by say 4 to 6 months in launching your new product. So you cannot afford, and you also cannot afford to launch a poor quality product, and that is where the DOE comes in picture. You need basically 4 set of skills in conducting DOE: planning skill, statistical skill, teamwork skill, engineering skill. It's a cross-functional approach. You need to have the people from production, procurement, design, manufacturing, and then only you can set a right premise for conducting DOE, and then you can really conduct the meaningful experimentation. So once again, I would like to remind you, all experiments are designed experiments. Whatever way you want to do some experimentation, intuitively there is some design involved, but some are poorly designed, some are well designed. If you want well designed, take the help of DOE. There are key terminologies: effect, so relationship between factor and the response variable, that is the output variable that shows the observed results or I am interested, like productivity, yield of the agriculture. Observed value, particular value of the response variable determined as a result of test. Factor, it's an independent variable. Assigned cause that may affect the response, and noise factor, independent variable that is difficult to control or too expensive to control as a part of standard experimental condition. There are some important terms before we finish. Level, setting or assignment of factor at a specific value. For example, temperature, we had seen the example of detergent say versus temperature and its impact on the ability to remove the dirt. So here your temperature is set at 3 levels: 10 degree, 25 degree, 50 degree. So these are the levels. Treatment, specific setting or combination of factor levels for an experimental unit. So you are using a particular brand of the detergent and temperature, and then you are trying to conduct the experimentation for a particular combination, that is called treatment. N is experimental run. So in a single performance of experiment for a specific set of treatment combination, N represent the number of experimentals run, and you can determine this very easily. N is equal to L raised to F. N is number of run, L is number of level, and F is number of factors. So you can figure out that what could be the number of experimentation. So there are couple of terms, that is randomization, replication, and blocking. Randomization, run the experimental trials in random order so that bias can be avoided. Replication, sample size, or you try to replicate repeat measurement. And blocking, you would like to block couple of nuisance factors. So there are couple of tips to apply randomization. You think about the cost, setup time, and then you try to figure out that how the randomization can really help you. Replication is process of running the experimental trial in a random sequence. Here you are replicating in order to be more accurate in terms of your error with respect to your measurement system, and when you take the reading at different level, replication, if there is any bias possible, that can be captured. Replication and then repetition. Here I am not changing the setting, I am just repeating, so you may not be able to detect the bias, but this is less expensive, and for a particular setting you can repeat the experimentation and see that whether your system, instrument system is stable or not. And blocking, so there are many factors. We will see this concept in detail later on, that batch to batch production, shift to shift production, day to day production, I need to block them. Otherwise, if the homogeneity is not maintained, then my experimentation result will drastically be affected. So many times, suppose I am purchasing the material from different vendor, and one vendor is not capable to supply the entire material, then I have to block this effect. I am running the production in shift 1, 2 and 3, and suppose I proved the null hypothesis that produce of shift 1 in terms of quality is not equal to shift 2 and shift 3, then I need to block this factor. So you can see one example. A metallurgist wants to improve the strength of steel product. 4 factors are being considered for the experiment that might have some impact on the strength, and it is decided to study each factor at 2 levels, low setting and high setting. 8 trial experiment is chosen by the experimenter, but only 4 trials are possible to run per day or per shift, so each day can be treated as a separate block. I have put another example where you are having the batch to batch variability, and that needs to be blocked. So finally, strategy of experimentation, it may be the intuitive based guess, may not yield the concrete result. One factor at a time, I am just changing one factor with respect to the initial setting, we will see it, and then I will change the another factor by keeping the other factor with respect to the initial setting. Suppose you have set both the factors initially at the low level, then you change another factor, let us say factor 2 to higher by keeping the first factor at the initial setting, that is low level. Similar way, when you are changing the first factor to higher level, keep the other factor at the low level, that is the initial setting, and this is called one factor at a time. And then you have Fisher's approach. So there is a big say world of design of experiment, and this is what we are interested in. So think it over this situation. Suppose you want to compare the growth of garden flowers. I am giving you something interesting example with different conditions of sunlight, water, fertilizer, soil conditions. Complete the following steps as a part of DOE. Recognize and statement of the problem, selection of the response variable, choice of the factor, justify how will you consider the issues such as repetition, replication, blocking for this. If you do this, I think you are welcomed in the domain of your improve DMAIC phase, improve phase, and now you are entering into the world of design of experiment. So these are the references you use, and mainly I am referring the text Douglas Montgomery for this design of experiment discussion. So it's a systematic method to conduct the experimentation and figure out the impact of factors on the response right at the design stage. So thank you very much for your interest in learning this particular topic. Internalize it, revise it, have a good hold on the topic, and be with me, enjoy.